This is Clementine, and my name is Hannah, and I'm a postdoc at the Los Alamos National Laboratory. Our goal is to convince you that diamonds are a reactor's best friend as we describe a novel sensor that I'm developing to investigate high-valence actinides in molten salts to support the safe, secure deployment of molten salt reactors, or MSRs. A molten salt nuclear reactor is either cooled and or fueled by liquid chloride or fluoride salts. Especially in the case of salt-fueled designs, MSRs will be vastly different from traditional light water reactors in ways that will fundamentally change how we approach material accountancy and online monitoring for reactor safeguards. Plutonium monitoring is an essential component of reactor safeguards, and in an MSR it can move through a range of complex pathways. But the high-temperature, corrosive nature of flowing molten salts makes the detection and monitoring of plutonium particularly challenging. Electrochemical detection of plutonium has been considered in molten salts, but traditionally involves the reduction of plutonium. There are multiple issues with inducing this reaction, including the inherent phase change from liquid as an ion in the salt to solid metal, and the potential that would need to be applied by a sensor to reduce plutonium is very close to that of uranium reduction. As the primary fuel, uranium will overshadow the dilute plutonium and its signal will be completely hidden. However, plutonium-3 can also be oxidized to its 4+ oxidation state, which remains in the liquid phase, simplifying the chemistry, while occurring at a potential that is very different than the analogous uranium reaction. Metal electrodes are typically used in molten salts, but they are not sensitive enough to observe plutonium oxidation, and the electrode itself can begin to oxidize in the process. Diamond is renowned for its strength and resilience thanks to its crystal structure where all of the electrons are occupied holding the carbon atoms together, making them unavailable to participate in chemical reactions like corrosion. When diamond is artificially produced, impurities like boron can be incorporated to change the features of the material. Boron has one less valence electron than carbon, leaving electron holes in the lattice that allows the material to be just conductive enough to be an effective electrode while maintaining the resilience. Boron-doped diamond is a semiconductor that excels at oxidation processes where it can accept an electron, which is exactly what we need for our plutonium pursuits. Diamond may just be the key to unlocking higher oxidation states of actinides like plutonium that have not been well studied but are invaluable to understand for fundamental MSR chemistry needs. So, I am developing a compact diamond sensor optimized for plutonium quantification via oxidation. We have found that boron-doped diamond is exceptionally resilient in both chloride and fluoride molten salts, and has successfully observed uranium oxidation. Diamond is now being tested with plutonium to ensure it can provide continuous online detection for MSR fuels. A small versatile diamond sensor could be deployed at the various locations throughout MSRs where plutonium quantities must be monitored in real time. I hope I've convinced you that diamonds are a girl's and a reactor's best friend.